Okay, good evening, everybody.
Good evening, Professor.
And welcome to another session of organic chemistry. In today's session, we are going to start a discussion on Chapter 3. Chapter 3 is concerned with the chemistry of alkanes. Specifically, we are going to discuss the nomenclature of alkanes. And then we get to discussion of constitutional isomers, conformational isomers, and finally reactions of alkanes at the end of this chapter. But before we get the session started, let me make a couple of announcements. The next or the first class exam is scheduled for September 26th, which is about 2 weeks from today. And that exam will cover 4 chapters, chapters 1, 2, 3, and 4. Also, I want to remind you that the homework assignment, our homework assignment is due on Sunday, September 15 at 11 p.m. And for that assignment, you do not have to do those problems that want you to solve the acid dissociation constant. In other words, those problems that ask you to perform or calculate the acid dissociation constant, you do not have to do those problems. Okay, so to get the session started, do you want to discuss the you want to discuss the problem set that you did in the quiz? Okay, let us do that.
Yes.
Okay, Attila, can you go ahead and read this for us?
Which of the following species is a Bronsted acid?
Okay, thank you. Now this question says, which of the following species is a Bronsted acid? What is the answer to this?
Ammonium.
Ammonium. Okay, C. How many people got C?
Yeah.
Okay, that is correct. C is correct. Of course, you know, if you look, I will take a look at the choices that you have here. Only C, ammonium ion, has a proton to give. In other words, you have this here. So you have the ammonium ion. If we have a base here, say for example hydroxide, that will react with the ammonium ion to give ammonia and water. So therefore, what is the definition of a Bronsted acid? A proton donor. Excellent. In other words, a Bronsted acid is a proton donor. Any species that donates a proton is a Bronsted acid. And so what is a Bronsted base? Okay, so in this particular reaction here, which is the Bronsted acid going from here to here? Ammonium, right? Okay, so this is the Bronsted acid. And which is the Bronsted base going from left to right? Hydroxide. Now, supposing we want to go from right to left, okay, which will be the Bronsted acid? Water, exactly, because water will be donating a proton. This is water here. So in this case, the water will be your Bronsted acid, and the ammonia will be your Bronsted base. Very good. Okay, so let us go to the next one. Okay, Emeka, go ahead and read this for us.
Which of the following statements is not true about resonance structures?
Okay, thank you. Okay, so this question says, which of the following statements is not the true I mean, it's not true about resonance structures. Which of these is not true for about resonance structures? So what is the correct answer here?
C.
C. Okay. Do you all agree?
Yeah.
C. Okay, that is correct. Okay, why is C correct?
Because resonance structures are just different forms, and the true structure is just a fusion of all the resonance structures.
Okay, very good. So resonance structures are not equilibria. They are simply just a hybrid of the same molecule. Very good. For example, if you have this here, if I have this molecule here, okay, just to make things easy for you, let us number the carbon atoms here. Let us say this is carbon 1, carbon 2, carbon 3, carbon 4, 5, and 6. I could draw a resonance structure for that. What would it look like?
This is the same thing, just different.
What is the resonance structure look like? Give me the number to tell me where the double bond will be.
Alright, 6, 1, 6, 4, 5.
The double bond will be between 1 and 6?
Yeah, 1,
Okay.
6, 4, 5, 2, 3.
So the double bond will be between, this is 1, 2, 3, 4, 5, and 6. Say double bond is here. Okay, where else? Between 2 and 3, very good. And where else? 4 and 5, very good. So you can see here, these two molecules, they represent what we call benzene. If you notice here, the difference between these two molecules is the placement of those pi electrons. And so therefore we say these are resonance hybrid of benzene. Okay, these are resonance hybrid or resonance forms of benzene. Of benzene. Okay? So supposing if I did this, would that be true? Would that be true? No, that would not be true. That is an equilibrium. And that is what C is saying. In other words, resonance structures are not equilibrium. So we cannot say this, okay? So just know that resonance structures are not equilibrium. So you guys got that right. So let me go ahead and of course you guys know this is the double-sided arrow, the double-headed arrow, that is the symbol for resonance. Okay, next one. Okay, Akira, go ahead. Can you read this for us?
Write 2 additional resonance structures for the following molecules.
Okay, thank you. Say, write 2 additional resonance structures for the following molecules. Okay, to make things easy for you, since you guys are going to do this, let me number the carbon atoms. Let's say this is 1, this is 2, 3, 4 is here, 5, and 6 is here. Okay, let's draw the first resonance structure. What will it look like? What do you want to do?
Shift the double bond.
Shift
The double bond.
the pi electron to where? Give me the atom or the 2 atoms if you want to do that. Yes.
1, 2.
1, 2.
Yeah, 1, 2.
Okay, you want to place a double bond here?
Yeah.
So therefore you have to move the double bond between 2 and 3, right? Okay, very good. Okay, so now we move this to here, between 1 and 2, and then we move 1, 2, 3, and 4, and this to here. So that is, these two are resonance structures. Okay, can you give me additional resonance structure? Keep in mind, for resonance, all you are moving the pi electron or sometimes the non-bonding electron. Okay, so any other resonance structure? Yes, what do you see?
You can move the electron from between 2 and 3 and put it on 1.
Move the electron between 2 and 3?
Put it on 3.
Put it on 3. Okay, very good, very good. So you want, what you want us to do, this pair of electrons here, you want us to move it right here. Instead of moving it between here, right here. So just place it right here. Okay, very good. So that could be a resonance structure. Remember, I tell you to give me 2. I could have told you to give me more than 2. Okay, so this would be a resonance structure. Keep in mind, for resonance, what are you doing for resonance? Moving pi electrons or non-bonding electrons. That's all you're doing. Okay? Okay, if we do that. Okay, so this will stay right here, right? Are you seeing? Okay. And this will stay right here. And at this point, since you have moved this pi electron to here, this carbon now has non-bonding electron. And therefore, would that be a formal charge on that? Yes, because keep in mind, this carbon here has hydrogen, 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 also here, hydrogen here, and no hydrogen here. So we have this here. So therefore, what would be the formal charge on this carbon? Would there be a formal charge on that carbon? What would be? Negative, right? So this would be negatively charged. About this carbon? Positive, because you move the electron away from that carbon. Yes. You did not know you can do that. Now you know. Right? No, seriously. Seriously, for resonance, all you need to do is move pi electrons or non-bonding electrons. As long as that's all you do, then you have a resonance. Okay. No, but if you have any problem, see me after the class. Okay. Huh? Yes. I did not say that. I did not say that. Because those atoms that I've given you, the oxygen and nitrogen happen to have non-bonding electron. But if you move this electron to carbon, it becomes non-bonding electron. Okay, see me after class, okay? Any other question on this? Okay. Okay, so now you could also draw additional resonance structures. Just like we've done here. Between 2 and 3, you could move those pi electrons to any one of those other atoms, yes.
The way I did it was I did the bond between 1 and 6 and I put it on 6.
Between 1 and 6, yeah. You place the non-bonding electron on this here? Yeah. Yeah, you could do that too. Yeah. In other words, this is what you did. You move this to here, yeah. Right? That's fine. That's fine. Okay, since you move it to here, now you have this carbon as a pair of non-bonding electron, so that becomes negatively charged, right? Right? Is that right? Yeah. Okay. And then, of course, this here becomes positively charged, right? Okay. And so everything else is the same. This is right here and right here. Keep in mind you have all of these hydrogens here. Okay? Okay, so let us go to the last question. Okay, Ronald, can you go ahead and read this for us?
Acetic acid has a lower pKa value than ethanol, ethyl alcohol. What does this mean? Support distinguishes the appropriate resonance structure.
Okay, very good, and thank you. Okay, so acetic acid has a pKa value, has a lower pKa value than ethanol. So what does that mean? Acetic acid is more acidic than, very good. So it means this is more acidic. Keep in mind, the lower the pKa value, the more acidic the molecule is, okay? And this is less acidic. Now, we want you to explain that. Why is acetic acid more acidic?
Conjugate base is more stable.
Because, yes.
Conjugate base is more stable.
Excellent, excellent. Because the conjugate base is more stable. Conjugate base, keep in mind, let me write this. I want to write it for everybody again so that you, because this is very important. The strength of an acid, of a Bronsted, the strength of a Bronsted acid depends on the stability of its conjugate base. Depends on the stability of its conjugate base. Okay? So therefore, we then want to ask ourselves what will be the conjugate base of acetic acid. Okay? Okay, if you take acetic acid, anytime you lose the proton from an acid, the product that you get is what we call a conjugate base. Okay, so let us assume here that we lose this proton here. So we lose that proton. This becomes the conjugate base. That's for the acetic acid. Now, supposing we do the same thing for ethyl alcohol or ethanol. If we lose this hydrogen here, what do we get? We get what we call ethoxide. And that is the conjugate base of ethanol. This is the conjugate base of ethanol. Now the question is, why is acetic acid more stable than ethanol? So the answer to that, we have got to say that the conjugate base of acetic acid is more stable than the conjugate base of ethanol. Then the next question is, why is the conjugate base of acetic acid more stable than the conjugate base of ethanol? Does anybody know? Yes, Lona.
Because the conjugate base has resonance.
Exactly. Because we could stabilize the conjugate base of acetic acid with resonance. Okay? For example, we could take that. Let's take the conjugate base. We have a formal charge of -1 here. Okay, if we move this non-bonding electron here to form a pi bond between oxygen and carbon, then something has to give on this carbon, so we therefore have to move this away to oxygen. Keep in mind, every time you see a two-sided arrow like this in organic chemistry, what that tells you, we are moving two electrons. That is showing you electron flow from where the electron is to where you want to move the electron to. Okay. Okay, so in that case, we now get the resonance structure of the acetate. By the way, we call it the acetate ion. Okay, we now get the resonance structure of the acetate ion. Now this oxygen is negatively charged, and we have the pi bond to this oxygen. And these two here are resonance forms or resonance hybrid of resonance structures of the acetate ion. Okay? So therefore the answer to this is acetic acid is more stable than ethanol because the conjugate base of acetic acid is stabilized by resonance. Okay, that would be the answer. Yes, you have to write that. Okay? Okay. Draw the resonance structure and we need to explain that. Okay, if I give this to you in an exam, that's what I expect you to do. Okay. Okay, in the case of the ethoxide, which is the conjugate base of ethanol, we cannot draw a resonance structure. You can see that. That negative charge is residing only on the oxygen. We do not have a chance to delocalize those negative charge across the three atoms that we have, just as we have in this case, or in this case. Okay? Okay, so now we finish all the questions in the quiz. Is there any other question that you guys want to ask before we move on? Oh, yes, go ahead. Will it be possible to write? Oh, to write explain? Okay, yeah, I will do that. Okay, next time I will say explain. Okay, yeah, I think that's the same question that Kiara was asking, right?
No, because I said, what does this mean? So I put it was more acidic, but it says support the statement with the appropriate real-time structure. It doesn't say support with words.
Oh, okay. Okay, next time I will say explain with words. Is that okay? Okay. Anyway, let's move on. Okay, what I want to do now, I want to give you a little bit more information on chapters 1 and 2 before we actually move to chapter 3, because we will need this information in chapter 3. This is writing organic chemical structures. I know we've done some of this before, but I do want to reiterate this concept because they are very important going forward. Let's assume we have this molecule here. This is what we call a calculate structure. I also want to place non-bonding pair of electrons here. Or line bond structure. Whenever you write the calculate structure, I do want you to indicate non-bonding pair of electrons wherever it is appropriate. In this case, with oxygen. Notice in the calculate structure, you have to show all of the bonds to all of the atoms, right? Now, we could also write this structure in what we call a semi-condensed structure, in which we take a look at this carbon bonded to 3 hydrogens, just simply call it CH3, and then we show the bond between this carbon and this carbon, and then we have this here as CH2. I know we've done this before. Another CH2, another CH2, and then of course for you, anytime you have an heteroatom like oxygen and nitrogen, and you are drawing any of these molecules, any atom that has a non-bonding pair of electrons, you must show it, because it is very important that you do that. You get used to doing that, because when it comes to chemical reactions, those non-bonding pairs of electrons are going to be very useful. Okay, so this is what we call semi-condensed structure. Okay, we could then further condense this. Instead of showing this bond here, simply write this. Okay, each time you do this, show the non-bonding pair of electrons wherever appropriate. So we call this condensed structure. And then we could further condense this, in which we now write the skeletal structure. You notice we have 4 carbon atoms, so we could simply do this. 1, 2, 3, 4. Then oxygen is here, and hydrogen is here. This we call the skeletal structure. Notice in the skeletal structure, you do not show the carbon atom or the hydrogen atom attached to carbon. In the skeletal structure, the end of a line is a carbon atom, and the intersections of 2 or 3 lines is also a carbon atom. So this is a carbon atom here. This is a carbon atom, carbon atom, carbon atom, and carbon atom. And since we know that carbon is tetravalent, you then have to assume that this carbon here has 3 hydrogens in order to make for the tetravalency of carbon, and this here has 2, this here has 2, 2. Okay? That you have to know. Now there is another form of writing structures that I've not told you before, and that is this here. What we call the Lewis structure. In the Lewis structure, you have to show all of the bonding electrons. For example, here, between this carbon and this hydrogen, you have 2 bonding electrons, so you have to show it. See? You also have to show the non-bonding electron wherever appropriate, particularly on those heteroatoms. So heteroatoms. So we have non-bonding pair of electrons here. So in the Lewis structure, you show all of the bonding electrons. Now, for this class, unless I ask you to do this in an exam, do not waste your time drawing Lewis structure. It's just a waste of, it's too much time. It's too time consuming. So, for the most part, what I want you to use, either use the skeletal structure, the semi-condensed structure, or the condensed structure. Those are the ones that I would recommend for you to use. Now, sometimes we use a combination of these type of structures. For example, I could write this molecule here. Yes.
So do you only use Lewis structures for heteroatoms?
No. For Lewis structure, what I mean is, for Lewis structure, you have to show all of the bonding electrons.
Okay.
Okay.
Yeah.
Okay.
What about heteroatoms?
But you also have to show the non-bonding no, because I'm sorry. Yeah, I have oxygen in here, because I have oxygen in here. Oxygen is an heteroatom.
Okay.
Yeah. Any atom that is not a carbon atom or hydrogen atom, we call them heteroatoms.
Is that relevant to the structure?
No, it's not. It's just nomenclature.
Okay.
Okay. Now, sometimes I could write this kind of structure. Okay, I say, okay, notice what I've done here. I've actually combined the semi-condensed and the skeletal. That is also acceptable for you. You could do that. Okay. Now, when you do that, keep in mind, you have to also assume the tetravalency of carbon. In other words, you have 2 hydrogen here, 2 here, 2 here, 1 hydrogen here, 2 here, and 2 here. Okay. Okay, is that clear? Now, the last set of structure I want to show you before we leave this segment. Supposing I draw this. Okay, this is what we call a wedge and dotted line. This is a wedge. Okay, let us say this is CH3 here. Now this wedge right here, the way you look at this, take this out of here. This here, that means the bond is going away from you. Okay. On the other hand, the wedge, for the wedge, that means the bond is coming at you. And the regular line, this here, the regular line, that means the bond is on the plane of the paper or the plane of the board, wherever you're writing on. Okay, so what we're giving you here is a 3-dimensional representation of those bonds that are attached to this carbon atom here. Okay, so sometimes we are going to use this kind of convention to write organic structures. Yes.
We always assume that the bond is a single bond?
Or which bonds?
The ones that are coming away.
Yeah, yes. They are all single bonds. Yes, they are all single bonds. Okay. Okay. Is there any question on this? Okay. Okay. Now let us finish up on, remember I promised you I was going to finish up on acid-base reaction when we left the last time. We will do that, then we'll go to chapter 3. So let us call this conclusion of acid-base reactions. Okay, I know you've seen this molecule before. Acetic acid. Reacting with hydroxide. We get the acetate ion. Okay, let me get in the habit of showing all of the bonding electrons, since I wanted to do the same. The non-bonding electron. Okay. So now we get that, and of course we get water. The acetate ion and water. We told you, we gave you a table of pKa values. We know the pKa of acetic acid is about 5, let's say 5. And on this side, since this is the other acid here, the pKa is about 16 for water. Okay, now what I want to tell you now is very important. For all acid or Bronsted acid-base reactions, the reaction will go from the direction of the stronger acid to the weaker acid. That is the direction of this or Bronsted acid-base reaction. Always goes from the direction of the stronger acid to the weaker acid. In this case, this equilibrium will go mostly to the right. There might be a little bit of reaction going to the left, but most of the equilibrium will favor the forward reaction. Okay. Now, having given you that, let us do a problem. Let us do a problem. You got it? Okay. Huh? I say what? Oh, the direction of reaction in all Bronsted acid-base reaction is from the stronger acid to the weaker acid. Okay?
That arrow right there,
this arrow simply tells you that most of the reactions go to the right, because that is the direction of the weaker acid. And I also show you that you might have a little bit of it going to the left. Okay, having given you that information, let us do a problem. Okay, Shante, can you read this for us?
Which of the compounds above are strong enough acids to react almost completely with hydroxide?
Continue.
pKa or with a bicarbonate ion.
Okay, thank you. Okay, now what we're giving you here, the question this is which of the compounds above, in other words, these compounds here, are strong enough acid to react almost completely with hydroxide ion, giving you the pKa value of water, or with bicarbonate ion, also giving you the pKa value of carbonic acid. Okay, that's a question. What I want to do, I am going to do this here for you, and then I will leave you to do the rest of it. Now, this is a loaded question. Okay? This is a loaded question. But it does require that you think critically. This requires some critical thinking.
So you're telling us that's the answer, but you want us to tell you why it's there?
Huh?
You're telling us that's the answer, but you want us to tell you why it's there?
See, I said I was going to. I am going to do this, and then I want you to do the other two.
Oh.
Okay? Because you have 3 molecules here. They want you to determine any one of these molecules, which one of them will react completely with either hydroxide ion or bicarbonate ion. Okay? To do this, that means you must have some idea of Bronsted acid-base reaction. What they are really testing is your knowledge of Bronsted acid-base reaction and your knowledge of the pKa value. What is the significance of pKa value? Now they told you that hydroxide will react with any one of these. Of course, the hydroxide will be a base. If it reacts with any one of that, you're assuming that a proton is coming from any one of them to give water. And now they have given us the pKa value for water, which is 15.74. They also told you that the bicarbonate ion, which is this here, will react with any one of these to give carbonic acid, because that is what they're giving you here. Okay, assume that the proton is coming from any one of these species here to give carbonic acid. And they've given us the pKa value for carbonic acid, and that is 6.37. Okay? Okay, so let us do this here, okay, with hydroxide ion and see whether we can answer that question. So we have this. Another thing they've done here, they did a super condensed formula here. Okay? So what I've done here is to write it out in a calculate structure for you. Positive charge on nitrogen. Okay? Hydroxide comes here. Now what do we get? Hydroxide comes here. We plug this proton away from this molecule, and then we get this product. There's a pair of electrons left behind, and of course we have water. If you look at the reaction on the right, which is the acid, on the left to right, which is the acid on this side? This side, okay, this is the acid, and they gave you the let us see here, carbon, okay, right. They gave you the pKa value, which is 11.02, right? Okay, the pKa for this is 11.02. And then on the right side, which is the acid? Water. And what is the pKa of water? What is it? 15. Point. Oh, 15.74, okay? 15.74. So therefore the question is, which direction will this reaction go? Let me take this arrow out. Maybe I should not. Will it go to the right or to the left? That is the question they're actually asking. to the right. In other words, the direction of this reaction is here. Okay? So the equilibrium will favor going to the right. If there is a little bit of going to the left, it will be small. So in this case, we have now used the pKa value to determine the direction of a Bronsted acid-base reaction. So now let us do the same thing with the bicarbonate. Let us do the same thing with bicarbonate. Okay, I take this out. I place bicarbonate in there. And the acid that will be formed will be carbonic acid. Okay, what is the pKa of carbonic acid? 6.37, they gave it to us right here. So now the question is, what direction will this reaction go? Left or right? Left, exactly. Because you have carbonic acid is a stronger acid than this ammonium compound here. Okay? So those are the kind of problems you should expect using a pKa value to predict a Bronsted acid-base reaction. Okay. And finally, before we leave that, yes. Okay. Finally, remember when we started acid-base reaction, I told you there are two types of acid-base reaction. We gave you the Bronsted acid-base reaction. Which was the second one I gave you? Remember? A Lewis acid-base reaction, right? That was at the beginning of the discussion on acid-base reaction. What is a Lewis acid? Remember, what is a Lewis acid? Yes, Emeka. Electron acceptor. Yeah. Okay. Any species that accept electron is a Lewis acid, and therefore, any species that donates electron is a Lewis base. Okay. So if I have this molecule here, say I have boron trichloride. If you look at boron trichloride here, something is missing with this molecule. What is missing with this molecule?
Ooh, electrons.
Electrons. It does not obey the octet rule. Yeah. Even though it is a known molecule, but therefore it is very, very reactive because it is missing electrons. It needs electrons, therefore it will act as a Lewis acid. Okay? So if you have, say like water, water has non-bonding pair of electrons. So what can water do? Water could donate electron to this boron, and then what do you get? You get this compound here. Okay, now where are the formal charges? Let's start with boron. What will be the formal charge on boron? It's in group 3. Boron is in group 3.
-1.
+1, very good, +1. About oxygen. Oh, I'm sorry. Oh, I take that back. I'm sorry. I take that back. Sorry about that. Emeka, you are right. So that would be, in this case, that would be 3 minus 4. Yeah. Because it is in group 3 and it has right here. Group 3 means that it has 3 valence electron in its free state. And then right here, it has 4 electrons surrounding it. So that gives you -1. So the formal charge is -1. About oxygen. What will be the formal charge on oxygen?
+1.
+1. Okay. So this becomes your Lewis acid-base complex. Now, and this type of reaction will take place with any molecule that has non-bonding pair of electrons, with any Lewis acid. Okay. Another acid-base reaction. Supposing we have this Lewis acid-base reaction. Supposing we have this. Oh, okay, so by the way, right here, this is the Lewis acid, and this is the Lewis base. The water is your Lewis base here. Okay. What will happen here, this here, could donate electron to the proton from acetic acid, and this will release this electron to here, and then you end up with what we call hydronium ion. And this happens anytime you have a dilute acid in solution of water. This reaction takes place. Indeed, many times when in subsequent chapters, you will simply see us write, anytime we have a solution, say you have an aqueous solution of of HCl. HCl simply means water solution. What we do, simply do this. Write hydronium ion. In other words, since you have an aqueous solution of hydrogen chloride, HCl with water, it has to give you hydronium ion and chloride ion. And you will see us do this very in the subsequent chapters. We simply just call it hydronium ion. It becomes very useful. Okay, so at this point we have completely finished chapters 1 and 2, and now we are going to start whatever time is left on chapter 3. Oh, okay, I see I've got about 20 more minutes. You guys are trying to take my time away from me. Okay, now let us start with chapter 3, as promised. Okay. With chapter 3, we are going to deal with the chemistry of alkanes. Most of those things that we did in chapters 1 and 2, we are going to be applying most of those concepts in this chapter. Yes.
So the topics that you're checking off, are those the only things you're going to be testing?
Oh, no, we're going to talk about everything.
Okay.
Everything. So, yes, okay, we are going to discuss nomenclature. Okay, let me do that again. We are going to discuss the nomenclature of alkanes. Okay, we'll discuss our alkyl groups. we show you different classes of organic compounds. We also are going to discuss constitutional isomers, conformational isomers, and finally reactions of alkanes. And I think we should be able to finish chapter 3 in 2 lectures. Okay. Of course, this slide, as usual, you have a table of what I call the learning outcome objectives. You should use this here, this list of learning outcome objectives, as a study guide. In other words, these are some of those concepts that are very important for you to know. So I'm going to leave that for you. Now the question is, what are alkanes? What are alkanes? Okay, let me see if I call on somebody, if I can remember. Yes. What are alkanes? Right. Very good. Excellent. In other words, alkanes are compounds that contain only carbon and hydrogen atoms in which all the bonds are sigma bonds. In other words, all the bonds in alkanes are single bonds. Also, we also refer to alkanes as hydrocarbons, because they only contain carbon and hydrogen. As you can see here, we show you 4 examples of alkanes. You can see they only contain carbon and hydrogen, and all of the bonds are single bonds. Or sigma bonds. Because alkanes only contain single bonds, they are mostly non-reactive. They are relatively non-reactive compared to other organic molecules. Also, you will notice that alkanes are fairly non-polar molecules. Because they are mostly non-polar, some of their physical properties, for example, like boiling point and melting point, are generally much lower than other organic compounds. Say, for example, if you take a look at this molecule here, by the way, these are calculated structures of this molecule. And you also, I believe I told you before, that this mixture here, this is the mixture that you use for your cooking gas. Okay, now, if you take a look at the butane molecule, butane is a gas. Okay, the boiling point is -1 degrees. Now, if you compare these two, say like methanol, methyl alcohol, the boiling point of methyl alcohol this here is 65 degrees. In other words, methyl alcohol requires a lot of energy to break the bonds between individual molecules in order to go into gas state. But what we see with butane here, even though it looks like a bigger molecule, the interaction between different molecules are fairly weak. Okay? On the other hand, take a look at water. The boiling point of water is 100 degrees, very small molecule. Now, why do I give you all of this information? do that to introduce another set of concepts. Well, I'll tell you what. Which is called intermolecular interaction. These intermolecular interactions, these are not covalent bonds, but they are strong enough to impact on the physical properties of different molecules. We have what we call van der Waals forces. We have what we call dipole-dipole interaction. Also, then we have what we call the hydrogen bonding. For those of you in biology or in biochemistry, that is going to be very important, but particularly when you begin to deal with protein molecules. Let's start with water. If you take a look at the water molecule, how many of you swim? Most of you swim, okay? Have you ever jumped in the water with your face straight on? What do you get? You get a lot of resistance, right? Like you jumping on cement. Okay, you wonder, this is water, right? Small molecule, I should be able to jump into it and go through it. No, you cannot do that. Because those small molecules, they are bonded to each other, like a chain. Okay, and very difficult to break those chains. And that chain is hydrogen bonding. So you have another molecule of water here. This hydrogen here, is hydrogen bonded to this non-bonding pair of electrons. Keep in mind, this is not a covalent bond, but it is strong enough to impact on the physical property of these molecules. Then you have another molecule of water here. This we call hydrogen bond. This is called hydrogen bond. So if you have a pot of water, you want to boil it. Guess what? The energy that you are giving to that water is the energy that is needed to break those hydrogen bonds. And therefore, why does water have a boiling point of 100 degrees? And butane is a gas, which is -1. Because of those strong hydrogen bonds in water, you need energy to break them. Okay? So therefore, hydrogen bond is very important. And you get hydrogen bond anytime you have an heteroatom in a molecule, like oxygen, nitrogen, with non-bonding pair of electrons, and you also have hydrogen in that molecule, okay, attached to the heteroatom. Okay, in this case, if you have, in the case of ethanol, you could get hydrogen bonding also. Hydrogen bonded to this. And those are the energy that you need in order to break those molecules apart to become, to go in the gaseous state. Okay. So one of the reasons why the hydrocarbon or the alkanes are low boiling is because they do not have hydrogen bond. And also, they do not have, so now we know what hydrogen bonds are. Let me take that out. Also, they do not have what we call dipole-dipole interaction. In the dipole-dipole interactions, for example, if you have this molecule here, okay, would this be a polar molecule? What would be the direction of polarity? Towards chlorine, because chlorine has a greater electronegativity than carbon. Okay, so therefore, this is the direction of polarity. So we say this has a partial positive charge, this carbon, and this chlorine has a partial negative charge. So if we simply want to draw this as a, okay, just to visualize this, imagine that this is, no, maybe I need to draw that better. Think of this molecule here as, think of it as this here. Okay, so we say this part of the molecule has negative charge, this part of the molecule has partial positive charge. And you have a whole bunch of them. Partial positive charge, partial negative charge. Okay. Now, the attraction between this part of the molecule and this part of the molecule is what we refer to as dipole-dipole interaction.
So dipole-dipole is the interaction between the negative charge and positive.
Partial negative charge of a polar molecule. Okay. And those dipole interactions also impact on the physical property, like boiling point, of a molecule. But you do not have this in the alkane molecules. Yes. See that again? See that? I can hear you. Yeah. Yeah, where these two circles, they represent this molecule here. What I'm trying to do is to represent this molecule here. Okay, so we have the partial negative charge, partial positive charge. Okay, and therefore this here is the dipole-dipole interaction. Okay. Okay, so when we come back on, is it time? Yep. I see you guys are leaving. So when we come back on Tuesday, we are going to continue our discussion of chapter 3. So let me give you back your quiz. I do have your quiz here.
Oh yeah, one of them is negative and maybe negative.